Today we will talk about the use of hyperstability and positivity concept for the design of model reference systems. You already know that local parametric optimization could be used for this purpose. However, local parametric optimization does not guarantee the stability of the resultant systems. And because of this, there are cases when local parametric optimization works beautifully, and there are cases when it does not work at all. And then you understand that there is an approach based on the use of Lyapunov functions, and this approach could be successfully applied for design of the model reference system. However, this approach is excessively complex. It leads to analytical effort that is kind of beyond the paycheck of a control engineer. And therefore, hyperstability and positivity concept perhaps is the most rigorous on one hand and also usable by engineers technique for the design of a model reference system. The hyperstability and positivity approach is based on the conditions, on the enforcing conditions for global asymptotic stability on the model reference system. And if model reference system follows the conditions for global asymptotic stability, satisfies these conditions, we can expect so-called perfect asymptotic adaptation. And at the same time, the analytical effort is manageable in this case, especially since practicing engineers are welcome to use already existing cliches developed by professional mathematicians. The approach is this. We will convert a model reference system into a nonlinear negative feedback system. And then we will make sure that this nonlinear negative feedback system will be globally asymptotically stable. As I said, we have to take the model reference system and represent it as a negative feedback nonlinear system or system that will have linear time-invariant forward path and nonlinear time-varying feedback. In the forward path, we will have the variable v generated, and it could be, of course, a vector v generated, output of the linear time-invariant part, and this vector v will be used as the input for the nonlinear time-varying part, which will generate variable w, and this w with minus sign will be applied to the input of the linear time-invariant part. It looks like a control configuration. You may ask, where is the reference? Reference is 0 because the purpose of the system is to control the error or discrepancy between the model reference model and the adjustable system. Let's establish condition, or at least present condition, for the global asymptotic stability. As I said, these conditions were earlier obtained for control systems, nonlinear with negative feedback. The nonlinear time-varying part of the system must satisfy so-called the Popov integral inequality, which means that if you will take the input vector of the nonlinear time-varying system and multiply it by the output vector of the nonlinear time-varying part of the system, and product in and integrate this product versus time, the result of this integration supposed not to exceed some negative, finite negative quantity, gamma squared. Gamma is a arbitrary real number. Gamma squared is surely a positive number. With minus in front, it is surely a negative number. You know what we're talking about? We're talking about the integral of the product of these two vectors supposed to have low limit. This is what this expression defines. It is known, as I said, as Popov integral inequality, and any nonlinear time-varying part of the system that satisfies this condition is known to be hyperstable. Hyperstable. So our goal is to make nonlinear time-varying part hyperstable. The linear time-invariant part must satisfy the following conditions. First of all, if we would represent linear time-invariant part by a transfer function, h of s, this transfer function must be real for any real s. I guess it's a condition that is always assumed. H of s must have only left-hand side poles. The linear part supposed to be stable. And it also is not a big deal to imagine because it represents the reference model. And nobody would be using a unstable reference model. It surely must be stable. But the third condition is a little bit looks outlandish. For any real frequency, the real part of the frequency response of the linear time-invariant system should be greater than 0. And if this is the case, we call this linear time-invariant part strictly positive real. If I would apply the same condition 1 and the same condition 2, however, for any real frequency, real part of the frequency response is greater or equal 0, then the linear time-invariant part will be called positive real. And of course, our goal is to make it strictly positive real because we're shooting for the global asymptotic stability or perfect asymptotic adaptation, and it requires strictly positive real linear time-invariant part. However, linear time-invariant part could be represented by a state variable form. And in this case, if you have a linear time-invariant part defined by a state variable form, the transfer function definition it will be this. It will be h of s equal to G is some matrix filter, Si, you know what it is, minus Am in the power of minus 1. You may ask me where is matrix B that you always want to see in a situation like this. Matrix B is unity matrix. So this is the transfer function, but it is a state variable definition of the system. Matrix Am is nothing but the fundamental matrix of the reference model. And you understand that fundamental matrix of the reference model is expected to have all negative eigenvalues because the system reference model is supposed to be stable. If this is the case, if this is the definition, then G is a matrix filter, and in order to satisfy the conditions for being called strictly positive real, filter G must satisfy the Lyapunov equation. or must be defined by the Lyapunov equation. You saw this Lyapunov equation earlier. This Lyapunov equation says that if I will take this fundamental matrix AM transposed times filter G, G is a square matrix filter, plus matrix D times the fundamental matrix must be equal to minus Q, where Q is a positive definite matrix. And I am teaching this course for years, and I always use unity matrix for Q. So this is good enough and leads to simplest possible results. How would you find matrix D from this equation? Of course, using a software tool. And then you have to accept the following reality of life, that global asymptotic stability condition implies that linear time-invariant part is a strictly positive real, and you have the definition for the state variable case and for the scalar case. Nonlinear time-varying part must be hyperstable or must satisfy the Popov integral inequality. And then there is global stability condition, not asymptotic, but global stability condition. Linear time-invariant part is positive real, not strictly positive, but positive real, but nonlinear time-varying part is hyperstable. And then you may ask me where these mathematical formulations coming from. What is the rationale behind these mathematical requirements? You know, you have to visualize some sinusoidal signals that flow through the circuit of the nonlinear control loop, and by having these conditions, we are achieving such combination of phases in these sinusoidal signals that prevent signals from divergence. And I think this is probably the best definition or the best way to visualize these complex mathematical requirements. Let's talk about the design of a model reference system using the hyperstability and positivity approach. This design requires to perform 4 steps. Step number 1. We have to represent a model reference system by an equivalent negative feedback system with a linear time-invariant forward path and nonlinear time-varying feedback. And we will be considering several cases, several applications, and in each application we will start from creating this nonlinear negative feedback system. Condition number 2. We have to come up with an adaptation mechanism that would make nonlinear time-varying part or the feedback to satisfy the Popov integral inequality or be hyperstable. You know, the adaptation mechanism will be incorporated into the nonlinear time-varying feedback. And if we would properly choose, properly define this adaptation mechanism, then this feedback will be hyperstable. Step number 3. We have to assure that the linear time-invariant forward path is strictly positive real. How to achieve this condition? We have to introduce a special scalar filter if system is defined by transfer function, or a matrix filter that if system is defined by state variable expression. The matrix filter will be defined through the Lyapunov equation. For the scalar filter, Scalar filter will be just a polynomial, and you will see later how we will define this polynomial. Finally, after the linear time invariant part made strictly positive real, when nonlinear time varying part is made hyperstable, we have to go back to the original model reference adaptive system and explicitly specify the adaptation law. We have to get these results obtained for a negative feedback equivalent system into the original model reference adaptive system. Let's get into a numerical example. Actually, it's algebraic example, and it is a very simple example. For the reference model, I have this second order system. It's assumed that parameter B0 of the numerator, parameter A1, and parameter A2 are known to us. They are fixed. It's a reference model. In the adjustable system, we will assume the same configuration, but only the numerator, the gain in this transfer function, will be adjustable. So our adaptation law will be the definition of beta 0 as a function of error and time. As far as the inputs are concerned, input is the same for the reference model and for the adjustable system. Therefore, you can conclude that we're dealing here with a parallel configuration of the system. Theta model and theta system are two outputs, correspondingly output of the model and output of the system. If these two outputs are defined, we should be able to get this expression for the error, the discrepancy between the reference model and the adjustable system. It is very easy to define this. However, you see the typo here. We have this supposed to be theta system, not theta model. And I will fix it. And when you will see this hard copy, it will be fixed here. Okay? The next what I do some simple mathematical manipulations, and I am getting this equation. This is the differential equation, or S-domain equation, for the error epsilon, the discrepancy between the reference model and the adjustable system. Don't forget that this is theta of the system. This is expression for the error. The adaptation mechanism is right here in the definition of beta 0 as a function of error and time. Rho is the common input of the reference model and the adjustable system. You know, we have to impose certain conditions on the nonlinear part. And to make it flexible enough, we will define adaptation mechanism by this expression. It has the integral part and the proportional part. And they both depend not on error explicitly, but they depend on a variable v, And variable v is defined here. Now, what is beta 0? Beta 0 is initial condition for time-dependent parameter beta 0. Initial condition, right here. Now, as I said, beta will be defined as a function of v and time. Here they split time into a time as a real, as time as time, and the integration time tau. You don't have to do it this way. It's not necessary at all. But this is definition of this intermediate variable v. You see, the adaptation mechanism will not deal directly with error. It will deal with error, of course, but through variable v, and v is a function of error. What is DOS? DOS is a polynomial filter. Polynomial filter. And then we will introduce variable minus w1, which is equal to rho multiplied by the difference between beta 0, b0 and beta 0 as function of error in time. Let's look further. How the linear time-invariant part looks like. Linear time-invariant part is the transformation of variable w into epsilon. It defines epsilon as a function of w. And then it defines variable v as a function of epsilon. So if you want to get the overall transfer function of the linear time-invariant part, it is right here. It is v as a function of s divided by w as a function of s, and it is this expression. This is the transfer function that must be strictly positive real. Let's take a look at the nonlinear time-varying part that will convert variable v into signal w, and signal w with a minus sign will be applied to the linear part. This is the definition, and as I said, we using the integral part and proportional part in order to define variable coefficient beta defined as a function of error and time. What I have in these brackets is the difference between variable beta of error and time and variable b0 of the reference model. Okay, the minus sign is associated with minus sign in front of w. I don't think there is a algebraic problem in this expression. So the linear time-invariant part has been established. The nonlinear time-varying part has been established. Now our goal is to design our system, and to design our system we have to define appropriately filter d that is part of the linear time-invariant part. And these two expressions, psi1 and psi2, that you saw under the integral sign. You know that the Popov integral inequality for nonlinear time-varying part supposed to be like this. This inequality must be satisfied. How to satisfy this inequality? Obviously, we have only one choice here to define appropriately psi1 and psi2. Could this be done? Of course, this could be done. Now, I don't want to talk more than necessary about this. You have to agree with me. And if you do not agree with me, then you have to work through this algebra yourself. The point is this. If I would choose psi1 equal to a constant gain, positive constant k1, positive constant, and then if I would have v times rho, and if I would define psi2 equal to a positive constant k2 times v times rho, this requirement will be satisfied. Okay? You may check it for yourself, but this requirement will be satisfied. Now, this k could be positive constant. There is another suggestion to make k 1 minus exponential, but k2 must be constant. K2 even could be 0 in some cases, okay? Should be greater than 0, but it could be 0. The Popov integral inequality will be satisfied with this choice of psi 1 and psi 2. And if I would make this choice, the nonlinear time invariant part, nonlinear time varying part will be hyperstable. Yeah, there are typos here which I have to work on. In the hard copy, as I said, there will be no typos. All right, let's make sure that linear time invariant part is strictly positive real. How to choose this filter, polynomial g of s? The order for this polynomial should be system order minus 1. And since order of our system is 2, this is expression for polynomial g. It is d1s plus d0. If this is the case, the linear time invariant part will have this transfer function. This transfer function must be real for any real s. It is the case because all parameters are real, and therefore this condition would never be a problem for us. Now, what you have in the denominator is the characteristic polynomial of the reference model. Characteristic polynomial of the reference model must have all roots in the left-hand side. The reference model must be stable. So condition about not having right-hand side poles is automatically satisfied. And now we have to work on making sure that the real part of the frequency response of linear time invariant part is greater than 0 for any frequency. First of all, we replaced s by j omega. Then we multiplied this numerator and denominator by the conjugate. Look, when I replaced s by j omega, I'm having a complex expression in the denominator. You can figure out how the conjugate looks for this expression. I will multiply numerator and denominator by the conjugate expression of the denominator. This is what I will get. Then I will have to go through some algebra. And I have to make sure that this real part that I would extract from this expression would be always positive. How to make it happen? We don't have any special tricks about it. If I would make g0 equal to 1, for example, and g1 equal to or greater equal than a2 divided by a1, we're done. And there is nothing else to talk about. What happens now? I have the adaptation mechanism. This adaptation mechanism includes definition of the filter V, and I decided not to use the S-domain expression. I switched it to a differential equation, which is probably easy to implement. And I have this expression for the adaptation mechanism. You understand that this is psi 1 and this is psi 2. By the way, dt is missing here. I have to fix it. And these are the conditions for strictly positive real linear time invariant part. And these are conditions for hyperstable nonlinear time varying part. So the resultant system supposed to be globally asymptotically stable, or will possess the property of perfect asymptotic adaptation. Now let's apply this approach to design of a model reference state estimator. In the case of state estimator, we will assume that the reference model is a real physical process to be described mathematically. In this real physical process, we have this state equation. X dot x prime is equal to am times x plus bm times u. And we have initial conditions for value of the state vector at time 0. Now, matrix AM supposed to be unknown. Matrix BM supposed to be unknown. And I would say not unknown completely, supposed to be incompletely known. We're having the incomplete information about the matrix AM and matrix BM. And later I will tell you why we have to assume not completely unknown situation, but just incomplete information about the process. What is the purpose of the system that we want to build? To get estimate of the matrix AM and estimate matrix BM, and also create a system that could produce estimates for the state vector X. I want you to realize later we will be using state vector X in the adaptation mechanism, but adaptation mechanism very often does not require such sampling frequency as the control loop. So what we will do, we will create a way to provide information on state vector X with virtually any desirable frequency. The adaptation mechanism, of course, will be utilizing measurements of X state vector with the frequency that is available to us. The next expression is expression of the parallel adjustable system, which is simulation model with adjustable parameters. You remember this issue about the duality in model reference control. In some cases, reference model is a physical system. The adjustable system is a simulator with adjustable parameters. And in other cases, it is vice versa. For matrix Y of 0, I have initial conditions. For matrix A of system, I have initial conditions. For matrix B of the adjustable system, I also have initial conditions. Let me define the state generalized error. It is right here. The adaptation mechanism will include the filter that would convert error into variable v, into vector v. It will be error will be vector, obviously, and v will be also a vector. G is a matrix filter. And then the adaptation mechanism will include expressions or functions that define matrix A of the adjustable system as function of V and time, and matrix B of the adjustable system as function of V and time. And we use integral proportional expressions and initial conditions for this adaptation mechanism. You see, you understand that matrix AS is function of error in time, but we're not using error in its pure form. We use vector V that is defined as matrix filter G times error. So the adaptation mechanism works with variables, components of vector V. Our goal number 1 is to create, establish G filter, matrix filter. The matrix function phi1, matrix function phi2, matrix function psi1, and the matrix function psi2, such that as time approaches infinity, the error will be approaching 0. And it will happen, supposed to happen, for any initial conditions, x of 0, y of 0, difference between AM and AS of 0, difference between BM and BS of 0. In other words, we're looking for conditions for perfect asymptotic adaptation. There is additional statement here. This is supposed to take place for any piecewise continuous input signal U. I would replace it by verbiage for any realistic input signal U of t, because we will be working with realistic systems, and in any realistic system the input signal is expected to be piecewise continuous. All right, this was our goal number 1. We've been looking for conditions for global asymptotic stability or perfect asymptotic adaptation. Goal number 2, we have to satisfy some supplementary conditions to make sure that we indeed can accurately estimate matrix AM and matrix BM. In other words, the limit of matrix A of the adjustable system defined as function of V and T is indeed matrix AM, and limit of matrix B of the adjustable system is indeed matrix BM. Our goal number 1 will be achieved by choosing the adaptation mechanism. If we would properly choose matrix D, matrix functions, phi1, phi2, psi1, and psi2, we will achieve the goal number 1. The goal number 2 requires a little bit more complexity, and it will be achieved only if signal U would satisfy some additional non-trivial conditions. And I will present these conditions to you. Well, now we have to do these 4 steps. Step number 1, equivalent representation. We have to represent our model reference system by a equivalent negative feedback system, which is also a nonlinear system. So what we do, this is derivative of the error. For derivative of state vector x, we have expression. For the derivative of state vector y, we have this expression. and then we will add am times y and subtract am times y. It's only done for the sake of algebra. And finally, we will get this expression, this one. If you really want to, you can visualize this expression as the expression describing a closed-loop negative feedback system, if you want, because error dot is equal to matrix AM, fundamental matrix of the reference model, times error plus matrix B times control effort, if you want. Okay, but in reality, this expression is nonlinear. And not that simple. Now, if we will take a close look at this expression, at this equation, this is definition of the linear time-invariant part. In other words, in our system, we must insert matrix filter D that would pick up error vector and convert it into vector V. What is I times W? I guess this unity matrix plays the role of matrix B that we conventionally have in state variable control. And this is the external signal for the linear time invariant part, W1, the control effort. All right, this is the definition of the control effort. We call it W, it is equal to minus W1, and it's equal to what? I'm working on this expression now. Instead of A system, I use this part, minus AM, so I reverse signs in this expression, because we have a negative feedback system, by the way. And this part is represented by this expression, and again, the sign is inverted, because we're dealing with a negative feedback system. Something like this. The next requirement is to satisfy the hyperstability condition, or Popov integral inequality. And I do not want to do too many discussions about it, but matrix function phi 1 could be defined as positive definite matrix Fa that could be defined as a function of time, but we can use constant instead of this. It could be just constant matrix Fa. Then we have vector V, then it is multiplied by positive definite matrix Ga multiplied by state vector of the adjustable system, and this product is transposed. Similar expression is defined for phi 2, for psi 1, and psi 2. Okay, it is possible to realize by doing some mathematical exercises that if we would use this definition for phi 1 and phi 2 and psi 1 and psi 2, we will satisfy the Popov integral inequality by the system, by the nonlinear time varying part. You know, we can take it easy actually as far as matrix GA, GB, F prime A, F prime B, G prime A, and G prime B. First of all, we can always drop the parts of the expression that utilize these four matrices. These two matrices, we can have constant square positive definite matrices. And unity matrix would work perfectly for this application. And I will show you a numerical example where you will clearly see that although the mathematical definitions are complex, when it comes down to implementation, we can cut many corners. Step number 3, we have to obtain a strictly positive real linear time-invariant part. We do it by assuming this transfer matrix where filter D is a square matrix that should satisfy the Lyapunov equation. You see, although we're not using the Lyapunov functions, the Lyapunov equation still comes into play here. What is what? Matrix AM transposed is the transposed fundamental matrix of the reference model. Okay? Matrix D is a square matrix that is a matrix filter, converting vector error into vector V. For matrix Q, as I said earlier, I always use unity matrix with minus sign and place a minus sign in front of it. Step number 4 is return to the original system. Every element of the original system must be now defined using expressions for adaptation mechanism and using the definition for matrix D. The best what I can do now is to get with you into a numerical example. The reference model or controlled process is defined by this expression. This is matrix A, and this is matrix B, and we don't know matrix A very accurately, and we don't know matrix B very accurately. For the adjustable system for the observer, we have state vector Y, the same dimension as state vector X. We have adjustable alphas and adjustable betas. And this is a parallel configuration, as you can see. The same vector or scalar U is applied to both of them. Our goal is to build a online state estimator for the controlled process. Our goal is this, that as time approaches infinity, the discrepancy between state vector of the controlled plant and the adjustable system should be 0. And actually this should happen during the settling time. We don't have to wait for infinity. And it's supposed to happen for any initial conditions. At this point, I will use the best guess model of the process. Yep, I'm here. I'm using the best guess model of the process. I used canonical controllable form for the model of the process. And this is matrix B. I guess this is inconsistent with canonical controllable form. But at least matrix A has this familiar to you configuration. Now, I want to emphasize that this is only the best guess model of the process. This is the model that does not describe very accurately the process. It's only the best guess model of the process. Why do we need this model at all? Because we will be implementing this in the simulation. And in the simulation, I need some kind of reference model that would provide me the information, the state vector I have to pick up somewhere. Now I have to talk to you about the sticky point. It's really a sticky point. Matrix AM supposed to be used for solving the Lyapunov equation. And I have only the best guess matrix AM. So, unfortunately, this particular problem may or may not have solution. I guess the Lyapunov equation has enough tolerance built in it. But later I will show you how we can avoid getting into this sticky situation. Right now, let's assume that we still will be able to use matrix A of the reference model to solve the Lyapunov equation and obtain filter G. Let's take a look at the adaptation mechanism itself. The adaptation mechanism starts from conversion of the vector of errors into vector V, and we perform this conversion using this matrix filter. Okay, this matrix filter has to be designed. And this expression is part of the adaptation mechanism, of course. The next, let's make our life simple. And we will say that matrix FA and matrix FB are both equal to unit matrix, to unity. For matrix GA and matrix GB, we will have 0.1 times unity matrix. And matrix FA prime, FB prime, GA prime, and GB prime, we will turn into null matrices. So our adaptation mechanism will be quite simple. The next what you can see is the definition of matrix phi 1. Matrix phi 1 is equal to this matrix FA right here times V vector times Y transposed times matrix GA. And if you would go through all these matrix transformations on a element by element basis, this is the definition of matrix phi 1. So this, for example, is phi 1, 1. This is phi 1, 2, and so on. So I already have for you matrix phi 1. And this is matrix psi 1. It is built based on very similar assumptions. Certain matrices are zeros, certain matrices are unit matrices, and one of the matrices is equal to 0.1 times unity. So this is the whole story, and this is the definition of matrix psi 1 on the element by element basis. Don't forget, people, that I have to integrate matrix phi 1 and matrix psi 1 later. Now let's look at the linear time invariant part, that it's supposed to be strictly positive real, And to make it strictly positive real, we will do the Lyapunov equation. And I use the software tool to solve the Lyapunov equation. I don't want to solve it on the element by element basis, which is also doable, but software tool does a much better job and much faster job. So this is the definition of matrix D. It's a square matrix. I got this result by solving the Lyapunov equation using a computer tool, and for matrix minus Q, I used minus unity. And of course, the sticky point should be clear to you. Exact knowledge of the true fundamental matrix AM we don't have. And nevertheless, the solution is based on our best guess knowledge of the fundamental matrix AM. We'll fix this problem later in a slightly different modification of the design problem. Finally, we are ready to define the adaptation mechanism as conversion of error into vector V. This is the conversion filter. And then definition, every element of matrix A, every element of a matrix A of the adjustable system, and every element beta of the adjustable system. You know, I have here only the first column of matrix A of the adjustable system. And I have the only the first column of the matrix B of the adjustable system. Now, our best guess is used for initial conditions, obviously. For initial conditions, I'm using it. So, I do not anticipate any problem except the sticky point that I was talking about for building a very successful estimator of the state vector of the control plant using this approach. How about the convergence of parameter estimates? How about conditions for turning AS matrix of the adjustable system into matrix AM and matrix B of the adjustable system turning into matrix BM as time approaches infinity? You know, the condition that error is zero as time approaches infinity, it's a typical condition for perfect asymptotic adaptation. Unfortunately, it does not mean that discrepancy between matrix B and matrix A for the adjustable system and reference model will also approach zero. It's not true. It happens only under certain conditions. It will happen only if vector U and vector Y are linearly independent vector functions. How to achieve this linear independence? The reference model must be completely controllable. Components of vector U must be linearly independent. Each component of U must contain at least n minus 1, n plus 1 divided by 2 distinct frequencies. How do we approach this situation? Condition number 1 is checking the controllability, and you know it's done by building the controllability matrix and making sure that it is not singular, or at least the rank of this matrix must be equal to n. The next is covariance matrix of the input vector U should be built, and this covariance matrix should be a diagonal matrix. And condition number 3 you have to build fast Fourier transform of the particular components of the input vector, and you have to make sure that it has at least n plus 1 divided by 2 individual frequency components. I am not very much concerned about parameter estimation part, because later I will show you how to use recursive least square method procedure for parameter estimation.